Thank you all for joining today. For our webinar, we're going to talk about boosting the capacity of disaggregated optical networks, and specifically how you can use some of the latest multi-hall coherent technology to do so. I'm going to start out the presentation today and talk a little bit about the rise of disaggregated optical networks and what are some of the catalysts behind this transition. From there, we're going to move on to a discussion with Tom and Stefan, who are going to go into some of the underlying fundamental technologies and justifications for using disaggregation and multi-hall technology. And after that, they're going to conclude with some examples of how this technology is put into real-world applications. And then we'll wrap up with a summary, and there will be time at the end for questions. So I encourage you to ask questions as they come up during the presentation. So let's start taking a look at some of the investment catalysts that are currently in the market today, and disaggregation is really just one of them. And there's several other factors that are setting the investment direction of the industry. The first is 5G. There's been a massive amount of discussion about 5G, but so far its impact on the optical layer and the transport layer in general has been minor. When we've looked at some of the spending trends among the incumbents, among the operators that are planning to deploy 5G networks, the spending specifically associated with 5G is really yet to move the needle. When we look forward, the bigger impacts in the transport network with regards to 5G is more at the higher layers of the network, layer 2 and layer 3, and some of the switching components that are being put in place. There's also going to be some impact with fiber deep, and that's the second major catalyst. Fiber deep is the trend towards building high capacity optical networks closer to the edge of the network, to where the user is, to where the 5G antenna is, to where the fiber to the home PON OLT is. This was something that was really first initiated by the cable MSOs, particularly in North America, who are looking to drive fiber closer to their customer in order to improve broadband speeds. But in general, it's a trend that we see across many incumbent operators, all of whom are trying to use different types of PON or different types of switching architectures to achieve higher speeds at the edge of the network. The third trend, and this has really been ongoing since 2012, is the trend towards coherent. For example, Acacia started as a company in 2009, and we started to see the first deployments of coherent 100G systems in 2012. Since then, there's been over 1 million coherent ports shipped into the marketplace, and our forecasts are showing that during 2019, there should be around 500,000 physical ports shipped into the market. When we look at the catalysts and the trends in the 2018 to 2022 timeframe, the real focus is on moving to higher performance and higher speeds, particularly speeds at 400 gig and beyond. And we're starting to see the introduction of 600 gig systems, 600 gig capable systems this year. Another major focus is multi-hall, and this is making coherent more flexible so they can be used in a variety of reach and speeds according to the operator's needs. And this is another major trend in the coherent area that both Stefan and Tom are going to talk about at length. And finally, the next major trend that's coming in coherent is that of pluggability and the rise of technologies such as 400ZR and ZR+. That's not something that we're going to focus on specifically today. But of course, we will be talking about disaggregation. This has been a huge trend in the industry in the last few years. It started with the hyperscale operators who were seeking functional separation inside their data center networks. They wanted to essentially, build what they wanted, not necessarily what the vendors wanted to sell them. And so they went about designing their own systems, their own servers, their own switches inside the data center to build exactly what they needed. Now, they began to take the same concept and move it outside the data center. And that's where we started to see the rise of concepts like open line systems, where a single line system could accommodate transponders from different vendors. And perhaps the greatest challenge and something that the hyperscale operators had some advantage with, because they were starting fresh, is the orchestration and how to build the control systems to connect and control all of these individual parts from different vendors and different suppliers. So this interest in disaggregation, particularly among the cloud hyperscale operators, is really one of the reasons this is happening. Is there is an underlying shift in spending and where the money is coming from that's causing this to happen, and it's creating a greater focus on disaggregation and compact modular equipment. So if you look at this chart, this shows the percentage of spending in North America on WDM equipment from 3 different operator groups. And this is data that we compile every quarter and publish. And going back to 2014, you can see that spending by the cloud operators, and this is specifically companies like Google, Microsoft, and Amazon and Facebook, they spent just over 10% they accounted for just over 10% of all spending on WDM equipment. And since then, 2018, their spending is now closing in on 30% of the market. And by 2019, our forecasts indicate that spending from these cloud operators will account for more than 1/3 of all WDM spending. So this growth is causing the supply chain, both at the equipment level and the component level, to create greater emphasis on what these customers want. And by and large, these customers want disaggregated systems. This is a trend that's now starting to shift over to the traditional telco operators. And as you can see, their spending as a share of the total market has been in systemic decline. And in fact, in 2018, it dropped over 20% year over year. So despite a lot of discussion about 5G and bandwidth growth, year over year, the amount of money being spent by traditional operators such as Verizon and AT&T in North America is in decline. And at the same time, they're also looking to adopt and deploy the same techniques that the cloud operators are using in terms of disaggregation. So disaggregation isn't just about the cloud operators, it's about addressing the needs of the entire market, and everyone is really looking for ways to introduce these concepts into their network. So one of the results of this trend towards bringing disaggregation into the network has been a surge in compact modular equipment. Compact modular equipment were systems that were specifically designed for the needs of the hyperscale operators and their desire to deploy to use disaggregated techniques. Unlike data center switches and servers, the supply chain was successful in responding and building what the cloud operators needed. So for instance, even though you've seen announcements such as the Facebook Voyager, and there's been a lot of talk about optical white boxes and hyperscale operators building their own systems, for the most part, the equipment companies and their suppliers have built exactly what the hyperscale operators are looking for, and we classify this as compact modular equipment. There's a few examples on the right side of the slide of systems that we consider as part of this category. But over the last couple of years, starting in 2016, you can see how this type of equipment is now becoming a greater and greater percentage of the entire optical hardware market. So as the hyperscale operators have moved over to compact modular systems, the traditional telco operators are also moving over to this format. It's creating a major impact on the type of equipment that the supply chain is providing. And so overall, the growth in compact modular is an excellent proxy for tracking the growth of optical disaggregation. So at this point, I'd like to go ahead and hand it over to Stefan, and he's going to talk a little bit more about why operators find compact modular and disaggregation more attractive.
Yes, thank you, Andrew, and also thank you for the data that you presented. And before I jump into the introductory slides here, let me please reiterate, yes, disaggregation is often used actually in two definitions. One is separating the software from the hardware. So that's often then the bare metal switches that are running then a software on top that turns them into high performance data center switches, for example. In this presentation, this webinar, we clearly do not talk about separating the software from the hardware. We're talking about separating the terminal from the line system. So in disaggregated optical networks, it is, can we treat the terminal separate from the line system, and what can we gain by doing that? So the world likes to go open. The question is why? And I think the most obvious one is that there's different innovation speeds and life cycles of different parts in an optical network. So by recognizing that and trying to protect the investment that you have made, open provides a lot of advantages. On the lower left-hand side of the slide, you see that fiber typically stays in the ground forever, and operators are interested in utilizing that asset as long as far as they can. The line system technology, although there is innovation in optical amplifiers, Raman technology, ROADM technology, etc., line system also quite often stay in use for something like 10 years. And the shortest innovation cycle and the fastest innovation speed, if you want, is typically on the terminal side, the high-speed optics, the high-speed coherent optics, as we're going to cover today. So here, typically every 18 to 36 months, you see a new generation of technology that allows you to better utilize the available spectrum and to do additional things with the rest of the infrastructure, so the embedded line systems, and of course also the fiber where those line systems have been deployed. So being able to accommodate and recognize the different life cycles is the most important one. Of course, when you separate the terminal from the line system, you also are avoiding vendor lock-in. Ideally, you can mix and match a line system from vendor A with a terminal from vendor B. The smaller the packages are in terms of technology, the faster typically is the speed of innovation, the more flexible you are in evolving your network, and also you can compose a best-in-breed solution for every networking application out there. And clearly the advent of open source software and orchestration system takes care and helps with some of the concerns about how do I manage and talk to these open systems as I go forward. And again, progress in the open source standards and the orchestration systems are taking care of that aspect. Ultimately, the disaggregation and going open unlocks innovation, enhances the flexibility, gives you best-in-breed solutions, and avoids being stuck with a particular solution for an extended period of time. Good. On the next slide, we're going to see, actually, after this content slide, going to slide number 7, I'm going to quickly give you an overview about what are the 4 pillars of making disaggregation happen. So first and foremost, of course, is all about physical interop. Ultimately, we want to be able to send signals through that optical transmission system. And so that is key to making things happen. That's where we're going to spend a good amount of time on today's webinar, especially on the terminals with flexible baud rates, with programmable modulation schemes, fractional QAM, etc. So there's a lot of innovation and interop requirements happening in the terminals. Also, the line systems, in terms of being truly open, need to be actually considered as an important ingredient in the overall equation. Things like gateway functions to accommodate alien wavelengths are important. And of course, everything that we do in our industry should be standard-based in order to have physical interop. The second column, not a big part of today's webinar, but something we're going to mention later in the presentation, is the monitoring. Typically, monitoring was an important element and the key reason to go single vendor in a network solution. But we will see that especially that the DSPs in the terminals give you a lot of detailed information about not only the health of your terminal, but the health of the overall networking solution. It can be augmented by monitoring points from the line system. And of course, we need some northbound correlation. So monitoring is another important pillar in order to make a truly disaggregated solution function seamlessly. Third column, the control and APIs. Andrew indicated that programmability, open APIs, this is something that the hyperscalers brought to the industry. They have shown also the telco operators that by going to open APIs, you can actually take control of a lot of networking functions with your own software capabilities. So there's been a lot of progress here. And of course, we need control loops within the domains to make sure that we can do error allocation and fault location in case any problems arise. Last but not least, I want to add a fourth column to that. That is then helping us to build this house of an end-to-end service orchestration and network, and that is business partnering. I mean, as we progress as an industry, and as we are fewer and fewer vendors and system experts here in this industry, partnering is really important. So there's a lot of lip service out there. Everybody claims to be open, but when it really comes to then being open and transparent about physical parameters in the line system, physical parameters in the terminal, etc., sometimes we lack the transparency that is needed there, also the transparency for the planning data. So there's a business aspect and a partnering aspect involved in the whole concept of disaggregation that should not be underestimated. Good. With this overview, I'm going to quickly show you a typical network layout on the next slide. Of course, disaggregation is easiest in a simple point-to-point link, but as Andrew indicated, also the telco communication service provider part of the industry is very interested in separating the terminals from the line system and mixing and matching those. And their line systems, here shown on the right-hand side as a core OLS, is in most cases, especially when we talk metro or long-distance networks, not just a simple point-to-point link. It may be a ring or mesh topology. There may be multiple ROADMs involved, multi-degree network elements. And depending on the signal path that you choose through that network, path characteristics will differ, will change, and will actually then determine how much maximum capacity per channel and wavelengths you can send through any given path. Reason is that the OLS filters, the ROADMs are, especially when you cascade them, limit the signal passband, and it's important that the terminal interface is flexible enough, configurable at a very fine granularity to still make maximum use of the available spectrum that that path can give you. And we have seen in a lot of those brownfield installations where we used open terminals that typically 200 to 400 gig, even in old ITU fixed grid networks, are possible over long haul distances. So the goal is that with the new generation open terminals, you optimize the utilization of the spectrum over any optical path in any distance. And with that, I'll hand it over to Tom, who will tell us a lot about the technology advances inside the terminal that allow us to make those things happen. Tom?
Thanks, Stefan. As Stefan mentioned, I'm going to focus a bit more on the underlying coherent technology that enables these multi-haul solutions. I'd like to start by looking at the evolution of these solutions over the last nearly 10 years. Initially, the coherent solutions were fixed rate solutions, mostly based on 100 gig transmission in the early adoption for long haul applications. Then later, they moved, solutions started to be introduced that had multiple modulation formats supported, say QPSK and 16 QAM, that were able to address 100 gig and 200 gig requirements with common hardware. And this introduced the concept of trading off capacity and reach by varying the modulation format in a somewhat limited way. And these early solutions were typically operated at a single baud rate or maybe in some cases 2 baud rates, but fairly limited selection there. Today, solutions, as you see in this slide, can address modulation formats ranging from, say, QPSK all the way up to 64 QAM, which gives you the flexibility to support what we call multi-hull solutions. So you can support a wide range of use cases, everywhere from DCI out to submarine. But depending on some of the implementation details, this can sometimes lead to some limitations in performance. For example, let's start by looking at the spectrum. So if you have fixed or selectable baud rates, you may be able to choose a few different settings, but you're limited in your ability to adapt to the channel passband and really match the transmission to the channel characteristics. For example, if the transmission spectrum is too wide for the channel, then you end up with filter penalties. Or if the transmission spectrum doesn't fit the entire passband, then you're really underutilizing the channel and limiting your ability to fully utilize the network. In addition, steps in modulation format create a sort of quantization penalty that limits the ability to achieve full channel capacity. For example, when 4 bits per symbol isn't quite sufficient performance to reach the target capacity and reach, reducing the modulation order to 3 bits per symbol can result in a 25% reduction in capacity. So if we move to the next slide, these limitations can be overcome by continuously tuning both the modulation format and the transmission spectrum. By adjusting the transmission spectrum to match the available channel passband, you can get improvements in network utilization. At the same time, with our fractional QAM modulation, you're not limited to integer steps as you were in the previous example. Instead of choosing between 3 bits per symbol or 4 bits per symbol, a network operator can select, say, 3.8 or 3.9 bits per symbol, reducing the quantization penalty that I discussed on the last slide. So by combining fractional QAM and adaptive baud rate, you can work together to enable a flexible multi-hull implementation that can also improve performance. So we'll go into more details about how network operators can leverage these features in practical network applications later in the webinar. But before we do that, we'd like to just touch on briefly on some control and automation topics. So in the previous 2 slides, we talked about how the flexible transmission characteristics can increase network utilizations, but these advanced solutions also provide telemetry capabilities that can enable real-time optimization. So by utilizing performance monitoring features, the system controller can actively adapt the transmission characteristics, maintain high network utilization, and protect high priority traffic by reducing the link capacity when additional impairments may be introduced. So these advanced features and monitoring help enable network operators to reduce the inefficient margin guard bands that are typically used in today's optical networks, which results in improvements in network utilization. So I'm going to hand it over to Stefan so he can talk a little bit more about how ADVA takes these capabilities to develop a more advanced network controller.
Yeah, thank you, Tom, and thank you also for stepping us through some of the capabilities here that the Acacia technology brings to our terminal. And remember the 4 pillars of disaggregation that I showed at the beginning of the webinar. So clearly one of the important elements that comes to play when we make things work end-to-end is the monitoring. And the coherent technology gives us a lot more detailed parameters about the health of not only the terminal, but the entire link or network, including actually information then indirectly about the health of the open line system. For example, with coherent technology, you get the very detailed information about polarization effects, such as polarization dependent loss, polarization mode dispersion, and also quick changes in the state of polarization that might occur when lightning strikes. So these are all things that you can see with a coherent terminal and things that we're actually not easy to monitor in older generation systems. Even things like chromatic dispersion, which were compensated in traditional direct detect systems, now being compensated by the coherent receivers. And so that gives you directly information about the link length, and ideally the link length in terms of fiber plans certainly will not change, but there's always an unknown element of patch panels and inside central office fiber additions or subtractions that can be monitored through that. On the electronic level also, forward error correction, bit error rate, and Q factor, that gives you information about general impairments on your optical line, also signal to noise ratio, optical signal to noise ratio, any problems in terms of amplifier or the loss that you have in the network. And last but not least, error vector magnitude and SNR information allows you to drive conclusions about non-linearities and filter effects. So long story short, in a coherent environment with coherent terminals, the terminal alone can give you a lot of information about things that are going on in your line system and in your distributed optical network. So by reading and correlating that information, even if the line system is not from the same vendor, you can actually get a very comfortable and good view about the health of your end-to-end network. And moving on to the next slide, and that was then the third pillar, just the final word on what the overall end-to-end architecture looks like in such a disaggregated setup. So the line system, clearly that is what provides you with access to the spectrum. So when you say the end game is spectrum as a service, you can even envision having multiple line systems being interconnected, and entering and exiting such a line system is happening through a spectrum gateway. Typically, these geographically dispersed open line system implementations would be controlled by a domain controller or a traditional network management system, and then being reported upwards through a northbound interface. However, the terminals, they can actually feed directly into such a multi-domain SDN controller or orchestrator and be correlated then with the line system at that level. So the architecture again is simplified. No more lock-in into a single vendor network management solution that covers end-to-end. The terminals can feed directly through netcom or REST interfaces into the multi-domain controller, whereas the line systems will typically be still controlled through a domain-specific architecture and then feed northbound through a northbound interface. Good, enough about the overall networking scenario. Let's go back specifically now to some use cases that we have actually identified and trialed with partners in test or real life networks. So this slide provides you with an overview of the use cases we want to present. On the left hand, you see a very simple, I would say typical hyperscale point-to-point big fat pipe network. So you have fiber and you can utilize the fiber to the maximum without any restrictions, up to 1200 gig per channel. Typically you consume something in the range of up to 150 gigahertz in such a channel, and you utilize the fiber with close to 40 terabits per second. The middle one is what we call a flex grid brownfield. So this is a newer generation optical line system, may have multiple ROADMs, but with a flex grid implementation. And the goal is here to put the maximum capacity through the available spectrum. So these may be regional distances or long distance. Regional, you may go 16 QAM and achieve something like 800 gig. Long haul, you may just go to QPSK, doing 400 gig. Again, the goal here is that you utilize the line system with the flex grid infrastructure and maximize the spectral utilization there. And last but not least, there's still a lot of fixed grid brownfield networks out there. So typically built on the ITU defined 50 or 100 gigahertz passbands. Again, cascading some of those filters may lead to some passband narrowing. And again, the flexible modulation allows us to very nicely and flexibly fill the available passband so that we can achieve up to 400 gig in a 50 gigahertz wavelengths plan. Let's jump into, actually, I don't jump into that. I hand it back to Tom for highlighting some of the capabilities that matter the most when we talk about the metro DCI, or in general point-to-point DCI architecture. Tom?
Thanks, Stefan. And yes, as Stefan mentioned, we're going to go through each of those three use cases, and I'll provide a sort of background in the technology and how the coherent technology supports those applications. And Stefan will provide some background on some testing and trials that have been done. So first, we want to look at data center interconnects, or DCI applications. Whereas carrier applications might have a variety of different kinds of traffic, in data center interconnect, these applications are almost always utilizing Ethernet traffic. And the hyperscale operators tend to utilize the latest switches, which have support for the highest Ethernet speeds available. Today, this is predominantly 100 gig Ethernet, but over the next few years, it's expected to transition toward 400 gig Ethernet traffic. Network operators are looking for architectures that can cost effectively transport either one of these data rates. I think everyone knows that DCI applications place a high priority on cost per bit, but those DCI links also cover a wide range of reaches. Even though a lot of times there's a focus on some of the edge or metro DCI applications, and they receive the most attention, hyperscale network operators also need solutions that address regional, long-haul, and submarine requirements. So how do we address all of these? In edge DCI applications, those solutions, you want to utilize high capacity per channel using the highest modulation orders available. For example, a 1.2 terabit channel using 64 QAM modulation gives you compelling value in an edge DCI application. You look at regional to long-haul applications, the same network operators might use that same hardware to address an 800 gig channel where they can extend the reach by transmitting using 16 QAM modulation. And then for the most challenging links in long-haul and submarine, then you might use a 400 gig channel that utilizes QPSK modulation and the extra performance margin that allows you to avoid costly regeneration. So with an architecture that can combine flexible client interfaces with flexible transmission features, a well-designed multi-haul product can offer high performance in a wide range of network applications with the ability to optimize for capacity, reach, and channel characteristics. So I'll pass it over to Stefan to discuss an example of how ADVA has demonstrated these features in a DCI application.
Yeah, thank you, Tom. So clearly, again, DCI, can have multiple distances from shorter reach metro type distances all the way to much longer haul requirements. The trial that we're showing here was done at the end of last year. It was actually together with Tencent, one of the largest internet content provider in Asia. In this specific trial, actually, we were using their line system. So Tencent has their own line system, and the requirement was to utilize what they have developed. As Tom indicated, the hyperscalers always want highest capacity, lowest cost per bit. And so it was a requirement to determine as adaptive to their own line system. They didn't want any network management solution. It should be an easy API-based integration that we already covered. The fiber plant wasn't great in all cases, so the system had to be tolerant to very high fiber loss, and some value-added features like layer 1 encryption for enhanced security and also LLDP for the operational ease were required. We used our terminal here over a roughly 100 kilometer point-to-point link, came right up, was giving you the maximum speed at a very attractive price point, and so mission accomplished. These open terminals work even on, I would say, non-vendor supplied line systems, in that case, a self-created one by the internet content provider himself. Not much else to say about this. Again, a single point-to-point link, and I'll pass it back to Tom to lead us into slightly more sophisticated network topologies.
Thanks, Stefan. So next we want to talk about optimizing multi-haul optics for greenfield networks that utilize flexible grid spacing. As I mentioned before, the modulation and transmission spectrum can be continuously adjusted to increase channel capacity. But how do you choose the right combination for a particular application? As a general rule, the first step is to increase the baud rate to utilize the full channel spectrum available. Transmission spectrum can be fine-tuned to fill up the available passband of the channel, which mitigates the penalties that can result when the transmission spectrum isn't matched, as we discussed earlier. Next, you adjust the modulation format to provide the maximum capacity that can be achieved in the channel while maintaining target performance margin. By shaping this transmission signal to match the channel characteristics, we can improve the network utilization across a wide range of reaches. Now that we understand the benefit of increasing baud rate, we should consider how these greenfield networks might change in the future. Early DWDM networks utilized 100 gig channel spacing, but soon after 50 gig spacing was adopted to double the capacity using 10 gig transmission, which easily fit within a 10 gigahertz channel. Early coherent deployments operated in the 32 to 34 gigabaud range would still fit within these 50 gig channels, but development of higher baud rate solutions is leading network operators to increase channel spacing to 75 or 100 gigahertz. It's anticipated that further advances in transmission equipment will lead to the need to increase channel spacing beyond 100 gigahertz, but it's still preferable to maintain a spacing that fits nicely when combined with legacy 50, 75, or 100 gig channels. 150 gigahertz channel spacing seems to be a promising next step because it fits well with legacy channels at 50, 75, or 100 gigahertz, and it offers good alignment with transmission technology roadmaps. Now I'm going to pass it to Stefan, so we can discuss how these adaptive features can be demonstrated on a real network.
Yes, and actually here we are talking about a network trial that we showed at a recent event, the Terena Networking Conference 2019, together with our partners from Teleborgo, now Tele2. We built for them what is called the Baltic Highway, a long-distance network starting in Frankfurt and going all the way up to Tallinn in Estonia. The total length of that link is close to 3,000 kilometers. So when you loop it back from Tallinn to Frankfurt and back up again, you're getting close to 6,000 kilometer total distance. When we built that network, it was already at times when coherent optics had made their inroads in the market. And as Tom said, it was already desirable to no longer go fixed grid, but flex grid. So this is a true flex grid network that allows you to assign spectrum to your customer. It is predominantly designed to be a wholesale network, to sell spectrum as a service. And at the Terena conference, we showed how flexible we can use that now, depending on the reach requirements, by using these adaptive multi-hall coherent front end. So we trialed the longest distance, looping back in Frankfurt with 2.5 bits per symbol, giving you a total net data rate of 200 gig. Looping back in Poznan, that's in Poland, 3 bits per symbol, so slightly more complex modulation scheme, then giving you a higher net data rate, all the way up to 3.5, 4.5, and finally 5 bits per symbol for the shortest distance, which was still more than 1,000 kilometers. So I think when you look at the net data rate and the distances on the left-hand side, we were really able to maximize the utilization of the available spectrum in this flex grid network and achieve a phenomenal total data rate going through this long haul, or depending on your definition of long haul, even possibly an ultra long haul scenario here with close to 6,000 kilometers for the Frankfurt loop back. For us, it's really exciting to see that. In that case, we are actually supplying the line system and the terminal, but clearly there's no reason why that should not function on other flex grid line systems. So this new generation of multi-hall coherent optics is really giving you a tremendous flexibility and efficiency utilizing spectrum that you have available in these flex grid networks. And with that, I guess we already go to the next use case. Tom?
Thanks, Stefan. So the next use case is a fixed grid network. And in these types of applications, capacity can be limited by both impairments from channel filtering as well as noise from amplification. So even in the same network, the available passband for a channel that may pass through 2 ROADM nodes could be quite different from one that passes through 10 ROADM nodes. In addition, while ROADM technology is very advanced, there still can be small differences in each node in the filter shape and frequency offsets that make it somewhat difficult to predict the exact passband after traveling through multiple nodes. So traditionally, this has been addressed by adding additional margin or guard band to account for the worst case conditions, but that results in reduced capacity and lower network utilization. With transmission shaping capabilities, those extra guard bands can be avoided, enabling higher capacity transmission and improved network utilization. And I think Stefan has some examples about how these features have been demonstrated in fixed brownfield network applications.
Yes, actually, that's an interesting one. As I said during my introduction, that there's still a lot of fixed grade 50 gigahertz and 100 gigahertz networks with these filters and ROADM technologies out there. And the older the ROADM or filter technology, then the more likely you have this passband narrowing effect. Newer technology has steeper slopes. It's less developed, this narrowing, but still you will always have that. And so here we work with a European tier 1 telco. And the fixed grid network that was installed years ago. That's not an ADVA fixed grid network actually in this case. On the left-hand side of the slide, you see a long distance trial. So that's the backbone that was built with a 50 gigahertz grid for alien wavelengths. And we had 2 entry and exit points here. The first trial was 700 kilometers. We were going through 7 ROADM nodes. 5 were simply passed through, and 2 we added and dropped traffic. We were able to achieve a total of 300 gigabits per second per wavelength. So again, bear in mind that this network was designed for 10 gigabit per wavelengths. So that's a factor of 30 increase in capacity without touching any of the intermediate ROADM nodes and nor amplifiers or anything in that network really. We pushed it even further, going 1150 kilometers. In that link, we were passing through 11 ROADM nodes. 9 of them passed through, and 2 we did add drop traffic. Still 200 gigabits per lambda. So again, with this fractional QAM and adaptive baud rate scheme, we could transfer more capacity than any other vendor who participated in this trial over a third-party line system. And last but not least, with the same customer, on the right-hand side, there was a brute force point-to-point metro link, originally also designed for 10 gigabit non-coherent waves, included even dispersion compensation fiber in the link. And but again, fractional QAM, adaptive baud rate allowed us to put 600 gig through that link. Again, a link that was originally just designed for 10 gigabit per second. So long story short, with these new generation terminals and the flexible technology that Tom described inside those terminals, you can actually protect your investment, maximize the utilization of the available spectrum of the deployed line system, extend the lifetime of those line system, and also in terms of the time to upgrade, not a forklift for the whole network, just an upgrade or replacement for the terminal, or an addition of a terminal to wavelengths that are still not being utilized. And last but not least, I guess we said we're going to go through 3 use cases, but there's a 4th slide that we include here. And both of us, Acacia and also us with a partner for open subsea cables, that technology works really well also in submarine distances. And as our CTO would say, if it works well on submarine, you can pretty much do anything on a terrestrial network. Tom, is there anything you wanted to add to the submarine trials?
No, I think we've demonstrated. I think at the time we did, as far as I'm aware, I think it's still the highest spectral efficiency that's been measured on that link. So, flexibility and performance simultaneously.
Okay. All right, so with that, we're going to go ahead and start wrapping up the webinar. I wanted to give both Tom and Stefan a chance to talk directly about their products. And I also encourage all of you that are listening, if you have any questions, to use the interface to ask them. You can ask questions on things that were covered, and you can ask questions about things that you feel like we should have covered. We've already got a few of those coming in, so ask away. And with that, let's hear from Tom.
Thanks, Andrew. Our AC1200 solutions, based on our Pico DSP, enable the advanced features that we've discussed in this webinar in a compact modular form factor. The module supports 1.2 terabit capacity in edge DCI applications, 400 gig channels using QPSK modulation for the most challenging long haul and submarine links, and continuous tunability to match the transmission to any network characteristics. This multi-hull solution comes in two configurations. The dual channel configuration provides greater flexibility in brownfield architectures with 50 or 75 gig channel spacing. The SE squared configuration that we recently announced offers single channel operation up to 1.2 terabit in greenfield networks with channel spacing up to 150 gigahertz. With these two solutions, we offer the performance and flexibility to cost effectively transport 400 gig Ethernet traffic anywhere and everywhere. And with that, I'll pass it over to Stefan to say a few words about ADVA's FSP 3000 TeraFlex.
Yes, thank you, Tom. So our TeraFlex terminal using the Acacia AC1200 technology is seen here on the upper right-hand corner. So the product comes in a pizza box design, one rack unit, and you see it has a total of 36 QSFP interfaces. That's the maximum number of QSFP cages you can fit in that form factor. It's built into 3 sledges, and every one of those provides you 1.2 terabit line side capacity. It's using the variable modulation, fractional QAM, and tunable baud rate capabilities, so you can adjust into any spectrum, any wavelengths plan, and any network requirement with that terminal. The adaptation and open environment with the most modern APIs, data models, third-party agents, etc., is a given. Including some zero-touch provisioning capabilities. And also on the left-hand side of the slide, I want to point out that while the QSFP cage clearly was originally designed for a 100 gigabit plug, we have a micromux plug that allows you to break out 10 times 10 gig or 2 times 40 gig with another 2 times 10 gig out of the same cage. So in case your data transport requirements on the client side call for lower speed than 100 gig without any additional pre-aggregation box, you can actually do up to a 360 10 gigabit client ports with the same rack space consumption by using that additional plug. The box comes with line-side encryption. ADVA has been first to market, always historically, with actually transport layer built-in encryption, excellent availability feature, and the classical carrier grade with line side switchover, redundancy, in service replaceable controller, and the usual features that you need when you go into a carrier grade implementation. We believe the box currently is market leading in terms of the flexibility with client side interface support. Again, the line side capabilities and performance is outstanding and record breaking. It's commercially available. We've taken orders, shipped product, and we're certainly happy to ready for more business. And with that, back to you, Andrew.
All right, thanks again, Stefan. So a reminder, go ahead and ask your questions. For the operators that are listening on the call, I can see several of you out there. If you want to share what some of your greatest challenges implementing disaggregation have been, and ask some of these vendors about how they might solve those problems, those are great questions. We can also, is there anything that you need from operators to make disaggregation work better? And one question that we have here that's along those lines is that this presentation focuses a lot on the benefits and technology behind disaggregation. But it isn't always this easy, and there are business challenges that we face regarding buying open line systems. And so, how do you approach this, Stefan? I think this one is for you.
Yes, I think technically, as an operator, if you are buying an open line system, I think there's 2 things you need to watch out for and saying, is it really open, and is there any additional or hidden cost when you add a third-party alien wavelengths into that line system. So I think there's solutions out there that charge a alien wavelengths fee, for the lack of a better term, or a right to use for such a wavelengths that the line system provides. Clearly, if that is the case, make sure that is not a cost prohibitive limiting factor that locks you back into a single vendor solution. And of course, if you have existing line systems that you wish to upgrade, some of the older line system, although they may have been advertised as open, have proprietary vendor-specific like wavelengths tracker functionality. So if you enter that line system with a third-party alien wavelengths, like one of those new generation open terminals, you may run into issues that the line system actually doesn't allow that wavelengths to go through. So again, there's some proprietary roadblocks that have been intentionally built into some of the older generation line systems. There's ways to overcome them, but the vendor needs to cooperate. And when you buy a new open line system, I guess these are important questions to ask.
Right.
Other than that, I guess the more transparency you can have about planning parameters, etc., that always helps when you combine technologies from two technology houses.
Okay. All right. So we have another question. I think this is probably, it's targeted at both of you, but I think it's a better match for Tom. And that is in an ideal disaggregated environment, we would like to interconnect terminals from different vendors. And this person, they want to know is, are there efforts underway to make coherent optics interoperable? And are there costs associated with doing so? Like, what's your opinion on that?
Sure, Andrew. Yeah, there's quite a few efforts in the industry to standardize coherent interfaces, ranging from 100 gig to 400 gig. It started with the OIF effort a few years ago and 400ZR, but has expanded into Cable Labs and ITU and Open ROADM, and so a variety of different discussions going on about standardization. The initial effort was focused on limited use cases that were not so much trying to push the performance limits, but really focusing on low power. But if you look at something like Open ROADM, that has been a bit more focused on higher performance solutions and addressing carrier requirements. So standardization is really taking place across a wide range of different use cases. And in fact, we'll also be talking a bit more next week at ECOC about a new interoperable OpenZR Plus mode that kind of combines some of these different standardization efforts to address a high performance like Open ROADM, while being focused on the Ethernet type applications like 400ZR. So lots of activity going on in standardization. And I think standardization, I guess the second part of your question, I think it helps because I think it helps companies who are investing in this technology have visibility to where the technology and where the deployments are going to go. So it in some respects reduces the risk of investment by making it clear, where the right investment should be. So I think it's good for the industry.
Okay, great. So we have another question here from an operator in Asia, which I have to get to this question because they're up practically in the middle of the night, and that question's has to do with how in an open environment and using FlexGrid, how do you handle the any sort of optical channels, out of band optical channel communications? Is that something that will pass through the network? Is that something that you've dealt with before, Stefan? Taking care of these optical channels, the OCH, as it goes from terminal to terminal?
Yeah, so clearly, I mean, when you want to go to something like Spectrum as a service and as a wholesale provider, for example, you say, I want to give X amount of spectrum to my client, and then that client can utilize the spectrum to the max. You need to find a way to make sure that that customer is not utilizing more spectrum than you give him. So you need some sort of a spectrum gateway, which is something that we're developing. And I think that is a key element. I've shown it, but not discussed it much in one of the earlier slides, that when you even go from one line system to another, such gateways are needed in order to really then have a flexible entry point into a line system limiting the amount of spectrum that that particular user then can consume. And it is then up to the user to use something like an Acacia-based terminal or like the TeraFlex terminal, where you can say, okay, I have that amount of spectrum, I want to go this far, this is the best baud rate, this is the best modulation scheme to maximize the data throughput on that link.
Okay. I think we have time for at least one more question here, and I think this is a good one for both of you. Can you talk a little bit about how flexible Ethernet, has impacted your terminal design and also your DSP? And do you see benefits of using Flex Ethernet, and how do you expect that technology to evolve in the next couple of years?
You want to go first, or do you want me to go first?
If you want to go first, Tom, I'm not a Flexi expert, so I'm not sure.
Yeah, I guess I wouldn't be classified as a Flexi expert either, but I think it's one one approach to address how you match the need for flexibility on client interfaces and to the host interface with the flexibility that's inherent on the line side in these multi-haul applications. So I think it'll play out. I think there are other approaches that are also being utilized, and I don't think the book is fully written in terms of whether Flexi is the right solution in the long run. I think we're kind of in the third or fourth inning of a 9-inning baseball game.
Yeah, I guess then again I can't add much to the Flexi discussion. I think in general, as we talk here, terminals and line system, I think spectrum is pretty much the denominator that will be the currency of the future. And I guess those operators that know how to best utilize the spectrum and best sell the available spectrum are the winners. And Flexi is certainly an interesting way and concept to fill such a channel. But that's a little bit more, I would say, the client side of the terminal technology, less so the line side.
Okay. I think we have time for one more quick question. This is from a European wholesale operator, and they want to understand, in a hybrid modulation optical network, that is, using different types of modulation, all of these channels have different frequency width and different start and end points. How are people solving the provisioning problems? I mean, I think this probably goes back to, hey, if you're doing disaggregation, solving this problem is on you. If you want us to solve this problem, then you need to really buy a whole system. So when you see people using disaggregated networks, are they actually using implementations like this where they have hybrid modulation and a scattered network?
So I mean, from my perspective, it's still early days. So people are trialing to see what these new terminals can do in their installed networks. And I mean, what you typically try to do when we talk transport networks, yes, there's some dynamic reconfiguration, etc. But you have a certain idea about what path the signal should take, and then you say, well, this is the amount of spectrum I have available, and then this is the best baud rate and modulation scheme to utilize that. If that changes, or if actually the channel needs to be rerouted, I think in that case, with the adaptive technology that Tom explained, and I'm sure he can say a little bit more about that, then you say, oh, there's less spectrum available now, I need to throttle down the throughput. So there's going to be moments like that. But in general, I think this whole concept of this is the end-to-end requirement in my network, I treat it almost like a black box to say this is the amount of spectrum I have end-to-end, and then I tune, or actually this terminal is self-tuning to the best baud rate and modulation scheme. I think that automatic loopback and self-adjusting capability makes it a very viable and credible solution going forward.
Yeah, maybe if I can add to that, I think there's two general approaches. I think with FlexGrid technology, you can design the transmission and then adapt to match the ideal passband of the channel to the transmission. But the challenge of that is exactly what's described in the question. You end up with this fragmented network because the ideal channel widths are not nice multiples. So this is what I was referring to when I talked about 150 gig being a good next step, because it does fit nicely, and I think it's why adaptive baud rate is a critical feature, to be able to then match the transmission to the channel characteristics, because even when the spacing is the same, the usable passbands can be quite different between two different lengths. So I think all of those reasons are why we think these features are important.